Hello and welcome to online lecture 11, Collecting, Defining, and Sampling, Day 2. So last time we talked mostly about collecting and different ways of collecting data. Today we're going to focus on defining and sampling. So let's start with defining. Specifically, there's one term I want to go through and talk with you a little bit about. It's operationalism. And each concept should be defined by the steps or operations used to measure them. In other words, you want an operational definition. So when we talk about something, for example, like aggression, you might be able to break that down into different steps or different operations used to measure them. You might be able to come up with an operational definition. For example, if we were talking about aggression on in traffic, you might think of honking of horns, weaving in and out of traffic, maybe cursing at your fellow driver. There's several things I think you can come up with to kind of break that down and understand what it is. Other terms can be a little more complex, like attachment of a 5-year-old to their primary caregiver. What does that look like? How do you break that down? It's a little more challenging. Okay. Now, some people have posed objections to an operational definition because they feel that the demands of an operational definition are just too strict. And they're saying a single operational definition may not completely specify the meaning of a term, like, as we were just talking about, attachment. However, we can come back with that and say, well, we can have multiple operationalism. We can actually use multiple definitions, operational definitions, to help us understand a concept. For example, let's say we break out the term, she is a good salesperson. So we have this verbal statement, she's a good salesperson. And if we want to break that out, we might say she sells many cars, points out the positive features of the car, assists with financing, compliments customers. That could be our operationalization of she's a good salesperson. Okay. All right, so that's a little bit about operationalism. Now I want to turn over to talk a little bit about sampling. We'll spend a little bit more time on sampling today. Okay, so in order to talk about sampling and sampling methods, I want to make sure that we have a few terms all set and straight together. For example, sample. Sample is a set of all elements selected from a set of the elements that are selected from a population. Whatever set of elements are selected from a population, that's your sample. So what do we mean by that? It's really a subset of the population, right? It's a smaller subset. Now, we often hope that it is a representative set, but we'll get to that in a second. The population, however, is the full set of elements or people from which the sample was selected. So population might be the entire United States population of adults, right? And the sample might be 1,000 adults that you actually selected for your study. Okay. Now, a representative sample is a sample that resembles the population, whereas a biased sample is a non-representative sample. So we are always hoping that we get a representative sample, and we like to use random techniques, and we're going to talk about those in a minute, to help us get a representative sample. Okay, proximal similarity. Basically what we're talking about here is how similar our sample is to our actual population. What generalizations to people, places, settings, etc., that are similar to those described in the study can we make? All right. All right. Now, sampling error is the difference between the value in the sample and the value of the population parameter. So in other words, if you take a sample of energy levels, let's say, and you find in your sample that general energy levels have a mean score of about 90. Whereas in the population, you find that general energy levels have a mean score of about 100. Then your sampling error was about 10, right? 10, you were 10 off from the actual population. Just to give you a sense for what we're talking about there. Okay, a sampling frame is a list of all of the available items, elements, people, etc. in a population. That's who you can choose from. Right? So let's say you were doing a study of fifth graders, and you had a list of all the fifth grade students in a particular school. And maybe that list wasn't complete because maybe there's a few parents who said, never give out my name of my child for any studies. I don't want that. So your sampling frame would be the list that you have, the available children. Okay. And response rate is the percentage of persons selected to be in the sample who actually participate. Right? We're always hoping for 100% response rate, but we don't always get it. In fact, we rarely get that. Typically, there's only a % of people who we actually select to be in our sample that actually go ahead and finish our study. Okay. So now I want to talk a little bit about different methods of sampling. Okay. So let's start with the simple random sample. This is a method of choosing a sample in which each individual in the population has an equal chance of being selected. And it sometimes is referred to as the equal probability method of selection method, EPSOM. Each individual element has an equal probability of being selected into the sample. So how do you take a simple random sample? It's a lot of words, right? But how do you actually take a simple random sample? Well, this would be an example of putting all the names into a hat that you have. So let's go back to our fifth grade school example. We would take all the fifth graders that we have, put them into a hat, right? And then pull out a certain number for our sample. Now here's another way of looking at it. We have 12 people in our population. We reach into that population, and let's just pretend that instead of people, they're marbles, just to make this conversation a little bit easier. So let's say we have 12 marbles. 6 marbles are red. 3 marbles are blue. 3 marbles are green. So we reach into our bag of marbles and we pull out 4. Great. How did that work out? Well, it just so happens that we got 2 red, a green, and a blue. Isn't that perfect? Because 6 of 12 marbles in our population are red, half. 2 of 4 of our marbles in the sample are red, or half. 3 out of 12, or a quarter of our marbles are green. And here in our sample, a quarter of our marbles are green. And finally, 3 out of 12, or a quarter of our marbles are blue, and 1 out of 4, or a quarter of our marbles are blue. So it just worked out perfectly, but it didn't have to. See, with simple random sampling, we could have reached into the bag and pulled out 4 reds. We could have reached into the bag and pulled out 3 greens and a blue. Any number of possible things could have happened. Now, most of the time, when you reach into the bag and pull out a sample, you will get a pretty good representative sample. Most of the time, it will be pretty good. But if you wanted to assure that your colors here were distributed in the same way as your sample as in your population, well, there's another way to do that. And that way is called stratified sampling. See, stratified sampling is a bit different. With this technique, we separate the population into groups or strata based on some characteristic and then take a proportional simple random sample from each group. Okay, so first here, we're going to separate our marbles into 3 bags. A bag of red marbles, a bag of blue marbles, a bag of green marbles. And once we've separated our population out into those groups, we can select a proportional simple random sample from each group. So in other words, from our 6 marbles, we know we want to choose 2. So we reach into our bag and choose 1, 2. From our blue marbles, we know we want to choose 1. So we reach into our blue marble bag and choose 1. And from our green marble bag, we also want to choose 1. So we reach into our green marble bag and choose 1. And again, we're doing this so that just like in our population, half of our sample's red, a quarter of our sample's blue, and a quarter of our sample's green. So stratified sampling can be quite helpful when you're doing a study that has some groups that you want to break out into, and you want to make sure that you have a proportional sample of each group in your study. So let me give you a couple of examples where this might be true. Autism, for example, is more common, at least last time I checked, it was way more common in males than females. And I'd say the ratio is around either 4 to 1 or 5 to 1. Let's say 5 to 1 just for fun, just for right now. So if you chose, let's say 200 children diagnosed with autism to be in your study, if you just did simple random sampling, it's possible you could wind up with all males. If you want to make sure to have females represented in your study, you might be better off breaking your study out and choosing 5 times as many males as females. Okay. All right. Another example could be when you're looking, let's say at, you want to do a survey of APA presidents, APA past presidents. Well, that is another case where you happen to have more males than females. So you might want to break it out into different strata and then dip into each population separately to get a representative sample. Okay. And people will often stratify on things like age, gender, education, etc. Of course, the more strata you break into, the harder it is to actually you're going to have a lot more populations, a lot more groups you're going to have to sample from. Your groups might start getting kind of small to sample from. Okay. The next type of sampling I want to discuss is systematic sampling. Now this one's relatively straightforward. It's you choose every kth individual from the population, and the first individual selected corresponds to a random number between 1 and k. So in this case, we start with the number 2, and then we choose every third. So we choose 2, 5, 8, and 11. Notice that this would not be a good one if we wanted to ensure that we got an equally represented colors, right? Because we got 3 reds and a green. So we didn't get any blues here. We got too many reds, so it didn't quite work out that way. But it can be very good in certain situations. For example, let's consider the possibility that you're in charge of a factory, and the factory produces a certain kind of widget, we'll say, okay? And you're very interested in making sure that your widgets are all very well constructed, and you want to make sure that the machines, which do occasionally need calibration, are not operating below standards. Now, you could use a simple random sample, and it might tell you to select, okay, I'm going to look at product number 1, the first widget, the second widget, the fourth widget, and then widget number 1010. The only problem is if you check widget 4 and then you wait to check widget 1010, then in the meantime, if you see a problem at 1010, you got to go all the way back to 4 to figure out where the problem happened. Whereas in this case, if you took every 50th widget and checked it, let's say starting with 1, 51, 101, etc., then you only have to, if you find a problem at, let's say, 301, you only have to go back to 251 to see where the error started happening. Okay, so that's where it can be very helpful. Another example might be if you're doing survey sampling and you're trying to, you might say, I'm going to talk to every 5th person who walks by, right? Or something like that. Every 5th person I'm going to invite to take this study. Okay, something like that. It's not a very popular one in the behavioral sciences, but it can sometimes be useful. Cluster sampling. Cluster sampling is used when our population is already naturally broken up into groups or clusters, and each cluster represents the population. That way, we just select a number of clusters. So when you're thinking of cluster sampling, I want you to think of populations that are already naturally broken up, such as like neighborhoods, families, schools, classrooms, right? So let me give you an example. Let's first look at this one here. What they are saying is that all of these clusters that they have here, which are naturally broken up into 2s, are all equal. That's an assumption. So we can just choose 2 whole clusters. Notice when we choose this cluster, we choose everybody in it. Same with 11, 12, we choose everybody in this cluster. And then we can have a hopefully representative sample. Okay. Let me give you another example of this. Classrooms are great examples because that's naturally already broken up, right? So if you are looking to test an entire 5th grade, right? That's your population of interest, is entire 5th grade, and there are 8 5th grade classrooms. Maybe you just choose 2 of those classrooms, but then everyone in those classrooms gets your intervention or gets your test. Okay, so that would be another example. One more example. Let's talk, I know it's not happening right now, but let's talk about the buses around Westchester University. And let's say you're interested in finding out how people would rate their experience with the bus system at Westchester. Now, again, you could use simple random sampling. Choose the first person on a bus, and then the second person, and the 50th person, and you'll be hopping on and off all these different buses. But if you can assume that all your buses are pretty much equal, then maybe you just choose a bus at the beginning of the day, a bus at the middle of the day, a bus at the end of the day, and survey everyone on those buses, on those 3 buses you selected. So I want to point out an important difference between stratified sampling and cluster sampling, because this is where sometimes it gets a little confusing. Stratified sampling, you're breaking things up into strata. Cluster sampling already comes naturally broken up into clusters. Stratified sampling, you're choosing individuals within the strata. Cluster sampling, you're choosing entire clusters at a time, entire groups at a time, everyone being sampled in your cluster. That's the difference, okay? Hopefully that cements it for you. Okay, so these were our random methods of sampling. Now let's talk about some not so random methods of sampling. And these methods may produce a biased as opposed to not, or a non-representative as opposed to representative sample. First one is convenience sampling. Whoever is available, whoever happens to be first on a list, right? So let's say you are going to put up a new store. You're going to open a new store at the mall in the food corner there, and what you're debating between is a store that sells yogurt or a store that sells salads. Okay, so frozen yogurt or salads. And what you want to do is find out, well, which one would be more popular. So how are you going to decide which store to open up in your food court? Okay, let's see. Well, I happen to need to do some shopping anyway at Abercrombie and Fitch. So I'm just going to question people who are coming out of that store. I'll stay there for a while, question a few people, I'll call it a day. Now the problem is that may not produce the best sample. That may be quite non-representative, right? Because there may be certain characteristics to people who shop at a given store versus those who might shop at another store. I might be better off interviewing people at either the exits, because everyone who comes to the mall has got to use an exit, or at the food court itself. Okay. Quota sampling. Identifying quotas for individual groups and then using convenience sampling to select participants within each group. Now, this is very similar, as you can tell, to convenience sampling. The difference is I now have a certain amount I need to get. So let's say in this case, I'm interested in getting an equal number of, I want to get 100 males and 100 females in my study. Okay, and that's all I'm interested in. I'm not going to look at, I'm not interested in gathering other people at all. Just 100 of male, 100 who self-report female, and we'll call it a day. So then I would ask each person if they meet my criteria and I don't have enough, I would go ahead and include them in my study. If, on the other hand, I already have 100 males and someone else comes out of the store and they say they're a male too, I'm not interested anymore. That's it, because I already have my 100 males. Now, I describe it this way, and that's not putting it in the most favorable light, but there are times where quota sampling might make sense, right? When you are, for example, when you are looking to make sure that you're getting enough of a particular group in a particular sample, right? So convenience sampling is not ideal, quota sampling is not ideal, but like, for example, clinical trials might use some quota sampling. They might use some of these other sampling methods we're going to talk about too, but maybe they can only accept this many males, this many females into their study. They want to make sure those are equally represented, let's say. They might use that. Okay. Purposive sampling. This involves identifying a group of individuals with specific characteristics. Let's say you're interested in looking at college freshmen who have been diagnosed with ADHD, attention deficit and hyperactivity disorder. Now, you're ready, if you're going to do it at Westchester University, let's say, and we're only looking at college freshmen, and we're only looking at those diagnosed with ADHD, we've already got ourselves kind of a smaller population from which we're trying to get our data. we may need to get almost everyone that we can who meets these criteria. Okay. Snowball sampling. Now, this is a technique in which research participants identify other potential participants. It's particularly useful in identifying participants from a difficult to find population. Okay. So again, let's take a different example. Let's go back to autism. If you're trying to identify children with autism in a, let's say in a particular third grade of a particular school, that may be very difficult. So what you may do is start with one child, and you know the parent. And then that parent recommends and says, oh, I know someone else who'd be great for this study. Let me put you in touch with them. And he put you in touch with another parent. That parent says, oh yeah, can I invite my friends to participate in this study? Their children have, this person's child has autism too. And so on and so forth. So that's why it's called snowball sampling, because it builds like a snowball. Okay. All right. So while convenience, quota, purpose of snowball sampling are all non-random sampling techniques, and we may not love them, there are times when you might have to use these, and I do want to emphasize that, because there are times when you just have to accept, because you're going after a population that's maybe not easy to identify, that you might have to use one or other of these techniques. Okay. And that brings me to the next important point, and that's the difference between random selection and random assignment. See, random selection involves selecting participants for research from the population to be included in the sample. And the purpose is to obtain a representative sample. But random assignment involves how participants are assigned to conditions within the research. The purpose is to create equivalent groups to allow for the investigation of causality. So just because you don't have random selection does not mean you're not doing an experiment. It does not mean you can't get at causality. Okay, so in some ways, while they're both very, very important, when we're talking about experiment, when we're talking about causality, random assignment is a bit more important. Okay, so with random assignment, let's say we are trying to get a very hard to get sample, and we'll go back to our children with autism. Once we have our 200 children with autism of a certain age, then even though we got them through snowball sampling, we can still randomly assign them to our intervention or control groups. Okay. So we still might be able to talk about causality with this. All right. Determining sample size. How do you know what kind of sample you should get? Okay, well, it depends on a few things. More is almost always better. It's true. Unless you start climbing up into the millions, where you could have almost an overly represented sample. You could run into a few little issues there with statistics. More is almost always better. And in psychology, we usually don't have that problem, so more is pretty much always better. Okay. Effect size. How big of an effect do you expect to see? How big a difference do you expect to see between your groups? If you expect to see this huge difference between your two groups, let's say between your intervention group, your treatment group, and your control group, you don't need a big sample to see that. It's easy to see with a smaller sample. But if your effect size is kind of small, it's a subtle difference, you need a bigger sample to see that. The other thing to think about is what kind of power is required in your study. Now, as a golden rule, we like to have a power of 80%, which means 80% of the time, if there is an effect, we will find it. We will be able to see it. Now, that doesn't sound particularly high. You might think I'd like to have an effect size, a power of 90 or 95 or even 99%, right? If there's an actual effect out there, I want to see it. But when you get much higher in terms of power, it really drives up that sample size exponentially. So we tend to keep power around 80%. The type of statistic, when you're using simpler statistics, you don't need as many people as when you're using more complex statistics. And that goes into the next two, the number of variables and the number of groups that you have. Because the number of variables you have, the number of groups you have, all goes into the type of statistic, and that all, the more variables, the more groups, the more complex your statistic, the more complex your statistic, the more people you need. And ideally, to figure out if you're actually doing a study where you need to figure out how many people you'll have to know things like, what's your effect size? What statistic are you conducting? What power are you hoping to get? What's your alpha set at? And then you can absolutely, using a sample size calculator, get your sample size. Okay. That is all I have for you today. Be well, stay safe. I'll see you next time.